Okay, so we're going to look now in this video at energy in a spring. And we're going to remember that what we did is way back at the beginning, we had our spring, our loose spring, had a spring constant of 6.5 newtons per meter. I believe that's right. Yep. And then we said that we attached a mass of 200 grams, so 0.2 kilograms to it, and then it's stretched to 0.3 meters at equilibrium. And the time for the period t for one bounce we said was 1.116 seconds. Okay, so suppose we have we got four situations here. We have no mass, and then we have over here at equilibrium, and so this distance here that's 30 centimeters or 0.3 meters. And then suppose we gave it a little bit of just a nudge, so that this would be top, and we're going to say that that is, say, at 0.20 meters. And then so we nudge it up 10 centimeters. And then what's going to happen is it's going to fall through equilibrium, and it's going to get to the bottom, and it's going to be at this level here, 0.4 meters, because if I nudged it up 10 centimeters, it's going to drop down a corresponding 10 centimeters. Okay, so this is, so what we're going to do is we're going to say we're going to figure out the kinetic energy, potential energy, and spring potential energy at the top, at equilibrium, and at the bottom. And I think rather than cramming it onto that page, I'm going to go to another sheet of paper. Okay, so at the top, we know that the kinetic energy is 0 joules. That's really simple because it's stationary. The gravitational potential energy, we're going to say that I'm going to say that it is going to be 20 centimeters above the bottom, right? So I'm going to say it's 20 centimeters at the bottom. So 0.2 kilograms times 9.81 meters per second squared times 0.2 meters. And so I'm going to say the gravitational potential energy is 0.2 times 9.81 times 0.2. So I'm going to get 0.3924 joules. And I'm going to say the spring potential energy is going to be 1/2 kx squared. So my spring potential energy is going to be 1/2 times 6.5 newtons per meter. And now in this case, at the very top, the spring is still stretched by 20 centimeters. So it's still got that 20 centimeters of stretch in there. So 0.2 meters squared. So my spring potential energy is 0.5 times 6.5 times 0.2 squared. It's going to be 0.13 joules. And so my total E, my total energy is going to be that plus 0.3924 is going to be 0.5224 joules. Now we're going to say that's top, so we're going to say bottom now. We're going to say my kinetic energy again is 0 joules because it's not moving. We're going to say my gravitational potential energy is 0 joules because it's all the way down at the bottom. And we're going to say my spring potential energy is going to be 1/2 kx squared. So spring potential energy is going to be 1/2 6.5. But now at the bottom it's going to be 0.4 squared. And so my spring potential energy is going to be 0.5 times 6.5 times 0.4 squared is going to be 0.52. 0.52 joules, which is strangely enough what I got right there. So at the top I had 0.13 joules of spring potential energy, 0.3924 joules of gravitational potential energy for a total energy of 0.52. At the bottom I've got 0 kinetic energy, 0 gravitational potential energy, and my spring potential energy is 0.52. So now if we go middle, we're going to say that kinetic energy is something we don't know yet. We're going to say the gravitational potential energy is going to be half of that. So because we know it's going to be 0.2 times 9.81 times 0.1, so I'm just going to go 0.3924 divided by 2, and I'm going to get 0.1962 joules. And I'm going to go in, I'm just going to show you my spring potential energy is going to be 1/2 of 6.5 times 0.3 squared, because 0.3 was the equilibrium position, and so now I'm going to get 0.5 times 6.5 times 0.3 squared. I'm going to get 0.2925 joules. Okay, and so now what's left over? So what's left over is 0.52, well, let's call it 521 joules, minus 0.1962 joules, minus 0.2925 joules. And so my kinetic energy at the bottom is going to be what's left over. So 0.0323, so 0.03 joules. And so now if I plug that into 1/2 mv squared, I get 0.03 joules times 2 divided by 0.2 kilograms, and I take the square root of that, and I'm going to get my maximum velocity. It's going to be square root of 0.0, well, let's just take that answer, times 2 divided by 0.2. Maximum velocity is going to be 0.57 Okay, so there's an analysis of energy in a spring.